In this video, I will explain you the graph that represent variation of binding energy with mass number. So this is the graph. Here you can see that smaller nuclei like deuterium, tritium, helium, lithium, nitrogen that got comparatively lower binding energy when you are comparing with the highest binding energy, and also after certain point the binding energy decreases. So this is just a takeaway from this graph. Below a certain point binding energy per nucleon is less, and after certain point binding energy per nucleon is less. So first conclusion is most of the element in between mass number. So what is mass number? X is equal to A ZA. So this is the mass number, and I told you how to get the binding energy per nucleon. Binding energy per nucleon is equal to mass defect. So mass defect I am going to rewrite here. So Z into mass of proton plus A minus Z into mass of neutron. This is the total mass of the members of nucleus. Individual mass minus mass of nucleus. Now this is the total mass of the nucleus. So how does this nucleus is made? On combination of the nucleus is made. So while these members have combined and made a nucleus, certain amount of mass is lost. Okay, so this combined and form a nucleus, and there is a loss in mass that we will get from mass defect on subtraction of these two elements divided by total number of nucleons would be binding energy per nucleon. This is a very important concept. Mass defect divided by total number of nucleons, that is mass number, would be binding energy per nucleon. B energy. Okay, so binding energy per nucleon. BEN means binding energy per nucleon. BE means binding energy. Okay. Now see, here I have in the x-axis I have mass number, in the y-axis I have binding energy per nucleon, and which is measured in mega electron volt. So this is 2 mega electron volt, 4 mega electron volt, 6, 8 and so on. So see, here I could say that in between this, okay, from here it goes a maximum value and approximately till here. So if I am drawing a line, so that would approximately looks like this. So above these 2 points, approximately, that is in between mass number 30 and mass number 170, we have a region where binding energy per nucleon is almost constant with the maximum value. So this is the maximum value, and binding energy per nucleon is maximum with iron nucleus, and it is almost the same, or I could say that binding energy is a value equal to or greater than 8 mega electron volt. See, this is 8 mega electron volt. So in between these 2 points, I could say that the binding energy per nucleons is equal to or greater than 8 mega electron volt. This number is very important. Mass number in between 30 to 170. What does it mean? See, binding energy per nucleon is nothing but we have constituents of nucleus, and this on combination we got a nucleus. Okay, now a certain amount of mass is lost, and delta M into C square is the energy inside the nucleus, and that is binding energy. Now binding energy is also giving us a knowledge and information about how much force is required to break a nucleus. See, if I am able to give this much of energy to a nucleus, then I can break a nucleus into its individual constituents. So higher the binding energy, it is difficult to break a nucleus. Or I can say that that nucleus is highly stable. Lower the binding energy, we can provide the energy and we can break those nucleus. Maybe with high energy thermal reactor that might be possible. So anyway, lower the binding energy, I could say that easy to break a nucleus, or those nucleus has got lower stability. Okay, they would be subjected to reactions. Higher the binding energy, we need higher amount of energy to break the nucleus, so comparatively it will have higher stability. So here iron has got highest binding energy. That doesn't mean that iron is the strongest or most stable element in the universe. This stability basically would be defined against chemical reaction, and chemical reaction occurs due to loss of electron and gain of electron. Here I am going to talk about stability of a nucleus. So I could say that nitrogen, oxygen and carbon, these are stable, which means instability of a nucleus means carbon as an atom that is changing in that the carbon is changed to a different element. Say for example, carbon I am taking 1 kilogram of carbon and that is being changed to iron. This is called as instability of nucleus. That is, one nucleus changed to another nucleus to get stability. Okay, so this fact that iron is having the most stability for the nucleus doesn't mean that iron will not participate in any chemical reaction. So chemical reaction happen due to loss and gain of electron. Don't get confused. Okay, so you will get more idea when I explain second and third point. So one thing is very clear: below 30 and above 170, the binding energy per nucleon is less. So those nucleus are less stable, but in between 30 to 170, they are comparatively more stable. Okay. Now this unstable element can go to a stable condition. How is that possible? For example, see, helium is here having a value approximately 7.5 or above 6 mega electron volt as binding energy per nucleon. But at the same time, deuterium has got a value in between 0 to 2. I could say that here, if a hydrogen is existing as deuterium nucleus, then its binding energy per nucleon is approximately 1 point something. So I'll take 1 from this graph. But when it is being converted as helium, its binding energy per nucleon is 7 or 7.5. Say for example 7.5. See, this is less stable, this is more stable. How can this convert into this? See, hydrogen, deuterium is having 1 proton and 1 neutron. So this is 1 proton and 1 neutron. And one more deuterium atom, 1, 2, that is 1 proton and 1 neutron. And what about helium? Helium is having H2 2 proton and 2 neutron. See, this nucleus is having 2 proton and 2 neutron. 1 hydrogen, 1 proton, 1 neutron. It's not hydrogen, it is isotope of hydrogen, deuterium. So this is having 1 proton and 1 neutron. So 2 deuterium atoms, 2 deuterium nucleus, if they combine together, so 1 proton and 1 neutron, 1 proton and 1 neutron. So this is one nucleus, this is another nucleus. On combination, that will become 2 proton and 2 neutrons. Always an element would be represented by number of protons inside the nucleus. Now, how many number of protons are there? 2. Which element is that? It is helium. Now see, it has shifted from a lower stable condition to higher stable condition. This is called as fusion. So this is the reason why fusion reaction is happening. The reason is it would go from a condition of lower binding energy per nucleon to higher binding energy per nucleon, so that it attain nuclear stability. Okay, now this similar condition would happen in the case of mass number above 170. Above 170, for example, uranium. uranium is a bigger nucleus, and at the same time if a bigger nucleus split into two smaller nuclei each having mass number less than 170, then that would come here. Krypton, barium and all that would come here. So a uranium nucleus split into two smaller nuclei, and these two smaller nuclei will come here because their mass number would be less than 170. For example, 238 now has split into two nucleus of, for example, 150 and 138 each. Just for example, okay. So one element having a mass number of 150 and another element is having a mass of 138. Now 150 plus 138 is 238 itself. But anyway, 150 and 138 comes before 170, or those are having binding energy per nucleon greater than 8. Stable condition. Okay, so if this break into smaller nuclei, then these two smaller nuclei will come here, and that has got higher stability. Now I can say that energy is released when a bigger nucleus is split into smaller nuclei, and this process is called as, what is this process? Nuclear fission. Okay, so this is nuclear fusion. Here two hydrogen combine to form one helium, they fused. Okay, two hydrogen, this is not hydrogen, isotope of hydrogen, one deuterium and another deuterium, they combine and form a stable nucleus. This is nuclear fusion. Fusing is happened here. Okay, in the case of fission, a bigger nuclei is split into two smaller nuclei having higher binding energy per nucleon, thereby attaining more nuclear stability, and this is nuclear fission. Fission means splitting, fusion means joining. Okay, so these are very important takeaway from the graph of binding energy per nucleon. Okay, thank you.